think we move now to the both about the standardization of data formats in gamma ray astronomy, which will be led by Cosimo.
Okay, perfect. So I can start. We will present you today the effort of defining a standardized high-level data format for gamma ray instrument. And we will first present the format itself and then the projects that have successfully employed it. And to me, there will be Tarek. Tarek, are you online?
Yes, I'm here.
Okay.
Can you hear me well?
Yes, show yourself, please.
Okay, I was searching the Zoom window in my madness of... And now I have the video on, just so everybody can enjoy my face.
It's black. We cannot enjoy it, but okay, now we can see you. Okay. So yes, Tarek will help me with a session. If you have question and you are not in the Zoom, please do post them in the channel in Discord. And we would like to start asking you a few questions. Please raise the hand if you have expertise at all in gamma ray astronomy. So please attendee raise the hand if you have a basic knowledge of gamma ray astronomy. Okay, Bruno, Gernot, and Matthias. Okay, now raise the hand if you have an experience with data standardization in general with the astronomical instrument. Okay, only 1, 2. And last one, if you have experience with data standardization for gamma ray astronomy. Okay, so very few people. In general, it was 1 or 2 or 3 positively replying to the question. So I will start to share my screen. Can you see my screen? Can you see the screen?
Yes, Cosimo, perfectly.
Okay, so as I said, I will start introducing the format itself. So this data format for gamma ray astronomy instrument. So I always like to start this topic with this fresco. It's a painting by Raphael, and it's called the School of Athens, and it represents Plato and Aristotle having a discussion about the nature of things. And I'd like to imagine they're having a discussion about gamma ray astronomy. So Plato, believing in the heavenly nature of things, is pointing to the sky and suggesting to detect gamma rays with an orbiting satellite. And Aristotle, believing in the earthly nature of things, is pointing to the ground and suggests to detect the Cherenkov light from an electromagnetic cascade started by a gamma ray that hits the atmosphere. But despite the different philosophies, the two philosophers can actually speak the same language. And today in gamma ray astronomy, we are somehow in the reversed situation in which we have the same philosophy, same objective, but different languages. So it's more similar to the situation of the Tower of Babel, let's say. As a matter of fact, neither data format nor data model is shared by current gamma ray instruments, and multi-instrument analysis basically require custom expansion of proprietary software. This also means that if we want to release our current data, if we want to make a public legacy data release, then we would need to release our internal analysis tools that are not designed to be used by a large community. So let's see in general how the different gamma ray instruments deal with data standardization and data sharing. So Fermilat is the major instrument for gamma ray astronomy from hundreds of MeV to hundreds of GeV and beyond. And all data, in this case, in FITS format, are publicly available and promptly disseminated. And there is a web interface that allows any user to retrieve them. The open source, the science tools are open source and they are publicly available. And they also have a very nice Python wrapper that allow you to perform an entire analysis within a Jupyter notebook, let's say. This is The situation is very different for imaging atmospheric Cherenkov telescopes. Until the last decade, let's say, all our Cherenkov telescopes were operated as experiment. This means that they had order of hundreds of members, and the data access was private. In the same way, the analysis software. Also, the data format was custom. So each telescope has its own data format and software. And it's mostly based on root and C++ and root. This is because people involved in very high energy gamma ray astronomy are usually coming from particle physics. So they inherited this, setup of using C++ and root. But the next generation of Cherenkov gamma ray telescopes, the Cherenkov telescope array that is already in construction, will be operated as an observatory. It will have a much large number of members, thousands, and both its data and its science tools will be open to the astronomical community. And we will move to a FITS data format, at least the one that is proposed now, and to the tools that are currently in development and are candidates for to be science tools of CTA are written in Python, or they're written in C++ with a Python wrapper. So I want to stress that the operation of the next generation of Cherenkov telescope array poses these requirements. So on public analysis tools that you can check the GammaPy poster by A3, but also on standardized high-level data format. And this will be the topic of this talk. So members of the ESCT community channeled the discussion about this standardization in a forum. So there was an initiative to define this format that started in late 2015, and they come up with this solution. They created a forum that is basically a Sphinx documentation that is built via read the docs and that is contained in a GitHub repository, as you can see here. The docs contain the specification for the content, the naming scheme of the data. So the suggested support is FITS files, and within the documentation, you find the kind of data units, header, the column that you have to include in your file. And any change in the format is discussed via issues and implemented via pull requests. So anyone can get this chance to contribute to the format, provided that the community approves and supports his or her changes. So which data level do we choose to unify? A telescope of the current generation of Cherenkov telescopes produces an output that very roughly is of the order of terabyte per telescope per night. So very ballpark number. And this is the raw output of the DAX, so whatever event the data acquisition is recording. We choose to include, to reduce our data and to store what we call the data level 3 that consists of gamma ray candidates and response function of the system. Now, for the other astronomers that are not familiar with gamma ray astronomy, we detect, for example, Cherenkov telescopes detect also shower from cosmic rays. And also gamma ray instrument orbiting are affected by cosmic rays. So we have gamma ray candidates are events that have triggered the data acquisition and that we can safely identify with a certain confidence as being generated by gamma rays. And the response function, I think any of you is familiar with that. It's just the response of the system that we can factorize in 2 or 3 components. So this is what actually we store in the DL3 FITS files. So we have a data unit for the events. You can see it here. We have the ID of the event in the data acquisition, the timestamp of the event, the right ascension and declination, so the coordinate of each gamma ray in the sky, and its estimated energy. And then on the right, you can see the header data unit containing one of the IRF component, the effective area in this case. And in this case, it's just an array. You can see it here. Effective area binned in, so an array of values given certain bins of energy and theta, which is the offset from the detector center. So as I said, the initiative for this standardized data format is for the next Cherenkov telescope array, but actual current Cherenkov telescopes already can accommodate their data in this format. And also open source science tools, as I told you, GammaPy and Ctools are in development as prototype for the CTA analysis software. They can already read it as input, so they can perfectly operate with this data. So a bit of news about the current development in different experiments. So for what concerns spaceborne instrument, they have their own standardized. So Fermilab has its own standardized data format, but this data with few modifications can be made compatible with this DL3 data. And we will see it later, a project that actually does it. Then the current Cherenkov telescopes, all of them have an active DL3 group. Hess telescope was the first to actually make a public data release in this format, which will be the next topic in this talk. And then Fact, Veritas, and Magic released just a small sample of the Crab Nebula in this DL3 format for a specific project. And then the large size telescope, which is the first element of the future Cherenkov telescope array, has already started to test to reduce some of its high level data in DL3 format. Also, water Cherenkov telescopes with few modifications in their data can embed their data in this format. And I'm aware that there is a current effort in HAWK to produce a small test DL3 sample. So I will give you a bit of notions about what kind of analysis we can perform with this DL3 data, because later I will be talking a lot about Ambient and Binet likelihood. So I wanted to give you an idea of what it is. The objective that we have when we analyze the data is to estimate the flux as a function of energy of one or many sources in the field of view. So for what concerns the data reduction, we can do either 1D analysis or a 3D analysis. In the 1D analysis, you will estimate the spectrum of a single source in the field of view, and you will extract signal and background counts from the event list itself. So given the events that you have, you can see them here. You can see here the right ascension and declination of all the photons in an event list. You see that the cluster of photons of gamma rays corresponds to the source. So you will use this as a signal on region, and you will extract the background from another region not containing the source. So in this case, we integrate the spatial information in this way. We reduce the spatial information in this way. Or you can do a 3D analysis. So you will bin your data in right ascension, declination, and energy. You can see this image of a cube of an event list. But in this case, to perform the following analysis, then you would also need a background model of your instrument, because in this case, you will not be able to estimate the background directly from your data. And for the parameters estimation, we usually we either use an ambient likelihood. So given a field of view model, given a model of all the sources, positions, morphology, and spectra in the field of view, we can compute the likelihood of each observed gamma ray. Or we do a binned likelihood. It means that we bin the data in energy and coordinates. So we create a cube, as a matter, a binned cube. And then we compute the predicted counts in each of these bins, folding the IRF with the field of view model. So, so let's go to the project that actually employed the standardized data format. Let's start with the Hess first public test data release. So Hess was actually the first instrument to make a public data release among the ACT and to make it in DL3 format. A small dataset, 50 hours of early observation, were released with the purpose of software and analysis method testing. So not for scientific analysis, but to test the science tools, let's say, to offer an opportunity to test the science tools with current TSCT data, and also to support this effort for the definition of standardized high-level data formats. The release contains subsets of data that were already used in major publication, and each dataset represents a different science case. So we have the Crab Nebula, that is a point-like steady source of gamma ray. It's the brightest steady emitters of gamma ray in the sky. Then we have Blazar PKS 2155 that made an historical flare. So it's a point-like variable source with variable in time. Its flux is variable in time. Then we have a moderately extended source, steady with a constant flux. Then we have another supernova remnant with a large extension, a steady source. And then we have off data that you can use to build the background model that I showed you in the previous slides if you want to perform a 3D analysis. So you have seen already the type of data. So it's just event list and IRF stored in the data units. And this is what you can obtain with few lines of Python using AstroPy or one of the tools, GammaPy, for example. You can examine from the event list the spatial and spectral distribution of gamma rays from the Crab Nebula on the left, and from this extended supernova remnant on the right. You can see in the 2D plot, you can see all the gamma rays in the field of view. And on the right, you can see the counts as a function of energy extracted from this on and off region that I showed you before. And then the other element of the DL3 data are the IRF, and this is the effective area. This is an image of the array that is basically stored in the IRF component. So here on the left, on the bottom plot on the left, you can see the effective area as a function of energy at different offset. And on the extreme right, you can see the same plot, but made in two-dimensional. Okay, I think we can take a few questions because this project, this part of the talk concerns the data format in general. Then we will see how the data format was used to test the science tools. So I think I can stop for a second and take some questions if there are. So questions about the data format in general. Are there any? I'll stop for a second the screen share. Are there any questions on the data format in general? Doesn't seem to be the case, so I will continue. So, okay, let's check the project that have actually used the data in this format. So the first was, one of the first was the analysis of the HES public data release of the specific data release with Ctools, which is, I remember, used one of the candidates for to be the software of CTA, the analysis tool of CTA. It's published in astronomy and astrophysics, as you can see. So this HES test data release was analyzed with Ctools. It is the first test of these tools with actual EACT data because so far the tools were tested with CTA simulation. A background model is built from the off data in the release, and then they used in a 3D ambient likelihood on all the sources in the release. The consistency of the results is checked by doing a check against classical 1D Binet likelihood methods, because the standard method that we use with current generation of Cherenkov telescopes is the 1D Binet likelihood analysis. So, and this is also implemented in the science tools. So it was checked against this classical method and also against results from the literature using larger dataset from the same sources. And also there is a showcase of the multi-instrument capabilities of Ctools because Ctools relies on another library that is able to read different gamma ray data formats. So these are the results of a Ctools 3D ambient analysis on all the sources in the dataset using the background model built from the off. So you can see in each of the plot the spectral energy distribution. As I said, we want to measure the flux of the source as a function of energy. You can see in red the results that was obtained with Ctools, sorry, using the DL3 data. And in blue, in all the plots, you can see results from the literature using the custom software of the experiment and using a large data set. And despite the comparison is not exact because in the literature results, they used much more data. As you can see, there is a very general good agreement between the results of the analysis software that use the standardized data format and the classical analysis software of the instrument for all sources. So as I said, more test features of Ctools are tested with this data. In particular, they explore the possibility of fitting the extension of the Crab Nebula, which, as I said, is a point source for current Cherenkov telescope instrument, using this DL3 data. And then, as I said, Ctools are built on GammaLib, which is a library that is able to interface with different types of gamma ray astronomical data. So here you can see the result of a spectrum in red, computed using Fermilab data without converting them to the DL3 data format, original Fermilab data, with EACT DL3 data within the same framework. So with the same framework, you can combine different types of data and obtain these general results that is, as you can see, agrees very well with the other results from the literature. Another project that used this specific data release was this, and validation of open source science tools and background model construction in gamma ray astronomy. The scope of this project was slightly larger because this project tested both the candidate science tools for CTA, gamma pi, and ctools using this data release. The objective was to validate the tools against each other and also to validate a new background model template that is not relevant for this discussion. So the ctools and gamma pi were tested against each other, and this time they were checked not against the literature, but against the results of the Hess proprietary software. So against the classical software, that classical custom software that produce 1D spectral analysis. A new procedure, as I said, for the template background modeling is introduced, like in the previous paper, but this time they use a lot of more proprietary data to build the background, but still. This is used to test ctools and gamma pi 3D likelihood analysis. So this is some example of the validation against classical analysis methods. So you can see here a significant map computed with gamma pi in the background, and the Hess private software with the colored contours. And as you can see, there is a very good agreement between the two. So again, what is produced with the open source science tools relies on this standardized data format, and what is produced with a custom relies on the traditional root data. On the right here, you can see the results of a 1D binary analysis. So this is a classic analysis fitting a spectrum, a power law spectrum, to the different sources. You can see here the expression that we are fitting is just a power law of the energy with a normalization prefactor. And here you can see the result for the normalization in the right top plot, obtained in red with the Hess custom proprietary software, and in green and blue with gamma pi. And in all cases, the open source software using the DL3 data gets very good results. The deviation is always below 10%. Same for the spectral index of the power law. So as you can see, the classical methods implemented in these new tools are very efficient, and also the information that we are putting in our DL3 standardized data actually reflects what is actually contained in the original proprietary data. And this is very similar to the plot that I showed you before, but this time using the 3D likelihood of both tools. So in gray, this is always the spectrum of the 4 sources included in the data release. And in gray, you can see the results from the literature. And then in red, you can see the result of a 1D analysis performed with a private software. And in blue and green, a 3D analysis computed with performed with the open source analysis tools on the DL3 data. And as you can see, in all cases, there is a very general good agreement. The last project that I want to show you has still a bit larger scope, and it is to perform data combination fundamentally, and to show also how we can produce reproducible gamma ray analysis in gamma ray astronomy. So combining data from Fermi and 4 of the currently operating Cherenkov telescope in this preliminary DL3 format, we produced a joint fit of the Crab Nebula spectrum. We produced the first fully reproducible multi-instrument gamma ray analysis, relying only on open source software. All the material, data analysis script, and notebook are available online in this GitHub repository. And the purpose of the project is to show the ease of multi-instrument analysis once the data standardization has been achieved. So on the left, you can see the instruments that contributed to this project. We took 7 years of Fermilab data. As I said, they are freely available, and we performed just some small modification to make them compliant with the DL3 data format. And then each of the telescopes released a small sample of data in this standardized data format: 40 minutes from MAGIC, 40 minutes from Veritas, 10 hours from FACT, and 3 hours from Hess. And on the right-hand side, you can see the counts, the gamma rays coming from the source, obtained subtracting the background with the 1D analysis method I showed you at the beginning for each of the instruments. And you can see that we have a coverage of almost 3 orders of magnitude in energy with using all the instrument. As I said, Fermilab data are freely available, and we computed the IRF with the proprietary science tools, and then we make them DL3 compliant using GammaPy. And then we used a small sample of DL3 data that was specifically released for this project. So this constitutes also the first joint release of data by current Cherenkov telescopes. These are our results. So we did the spectral analysis. We extracted the spectrum of the Crab Nebula using 1D binary analysis, and we fitted this function that you can see here. It's a power law with an index that change with the energy. On the top panel, you can see the likelihood contours of the different parameters of the log parabola, the plotted against each other, the different combination of parameters. And you can see the power of the data combination in the reduction of the contours that correspond to the joint fit, which is indicated in red. So the different colors indicate the classical likelihood analysis performed on the single instruments, and the red one indicates the likelihood performed using the dataset altogether, okay? And here is the result plotted as a spectrum, let's say. So the parameters combined in the spectrum. Again, you have the same color code as before for the results coming from the individual dataset of the instrument, and in red, the result coming from the global fit using all the data at once. We plotted also a reference spectrum, obtained with a theoretical model fitted to the Crab data, just to show that we are in the, there is a good agreement with the result that we produce. This is the first spectrum of the Crab Nebula obtained combining Fermilab and 4 of the currently operating Cherenkov telescopes. But having the data in the same format offers also us the possibility to study the systematic uncertainties that affect our instruments. In particular, we try to cook up a recipe to estimate the systematic uncertainties in the energy scale, which we estimate is the effect that most that dominates our data, such a small amount of data. So we introduced a constant energy bias per each instrument, and we modified the assumed spectrum to account for it. So the spectrum will have a different Z for each of the instruments that are contributing to the fit. The global likelihood function is constrained with a normal distribution of this Z, and where the mean is 0 and the standard deviation is the systematic uncertainty that is claimed by each instrument. You can see here the same likelihood contours as before, using all the instruments together, and but this time including this systematic uncertainty. And this is the different Z factors for each of the instruments. And Fermilab claims an energy scale of 5%. So what we obtain with our fit is consistent with that. And in the same way for the Cherenkov telescopes, they usually claim a energy scale of 15%, and what we obtain is consistent with that from our fit. So as I told you, this was the first fully reproducible, we believe it was the first fully reproducible gamma ray analysis. How was this achieved? So for the short-term reproducibility, we released all the code and the scripts in GitHub. The data, as I showed you before in the screens, in one of the previous slides, are very small. Typically, it's hundreds of kilobytes per dataset, per DL3 observation, let's say 20 minutes of observation. So the global dataset, which is few hours per combining all the instruments together, is of the order of megabyte and can be shipped with the code. Then we have simple commands to reproduce all the results, all the tables and the figures in the paper, and notebook tutorials also. All the packages are managed via Conda environment. So you can just download the Conda environment corresponding to all the tools used in the analysis and reperform it. For the medium-term preservation, in case the Conda virtual environment is not enough to guarantee reproducibility, we have also a joint Crab Docker container, and we have also stored our results online in Zenodo. So this was the last project that I wanted to present to you, and I want to draw some conclusion. I think that the effort to define a standardized format for high-level gamma ray astronomical data is now fully recognized. Why? Because we had the first public release of VSCT data, of the current generation of VSCT data in this format by Hess and then jointly by the other ESCT. and also because having a standardized data format offered us the possibility to thoroughly test the science tools in development for the next generation of Cherenkov telescope arrays. And we see that the information that we embed in this data that we reduce in the standardized data actually allow us to perfectly reproduce the results that we have obtained so far with our own private software. Thanks to the data standardization, we can already produce gamma ray analyses that are multi-instrument, reproducible, and that rely on open source software. So I like to show this scheme because I think it summarizes the main points of our work. So once we have defined a common data format, then multi-instrument science is already possible because you just have to adapt the data of your instrument to this format. Then if there is an open source science tool that is actually compatible with this data format, that is able to read data in this format, then reproducible results are achieved without any effort. And this will be a key asset for the current and future instruments that plan to extend their data access to a wide astronomical community. And that was all for my presentation. And I think we can open the floor to discussion now. Okay. There is a question from Bruno.
Yeah, do you hear me?
Yes.
Yeah, thank you very much. So thank you a lot for this nice explanation of the goals of this common format. I just wanted to add one point is that so you are focusing on this event-wise data format that is, as you have well explained, the basis of multi-wavelengths, but also multi-messenger science analysis, because indeed detector like IceCube or Chem3Net could handle this kind of format to make joint analysis also. But just my comment was about about the output format of the science tools, which is out of the scope of your presentation. But I wanted just to say that also having a common format shared by the community at the level of DL5, so products like curve, maps, spectra, but in DL6 level also like catalog, will allow the community also to make to share results, to make a multi-instrument analysis, and this was also mentioned yesterday in a talk when people were using catalogs, and they mentioned that the difficulties they have to handle the data. What are the data? How and the understanding of the data, it takes a lot of time on manpower. So it was just a remark that maybe in the future we will need to also standardize the DL5 or 6 format for the community. But let's focus on the DL3 first.
Yes, thank you. Indeed, it's one of the possibilities also to extend it to the multi-messenger domain because the information that can be embedded is relatively similar. There is a question in the chat by Dirk, and I saw that Bruno has already replied to it. So Dirk asked, what is the size of this data set? And yes, you can see these are all the data contained in the first SDL3 data release. And as you can see, it's order of thousands of kilobytes per each of these run is 30 minutes observation. So then you can add them up. So I would say that the rule of thumb is 600-700 kilobytes per 30 minutes of observation, reducing the data to event list and IRF components.
Let me very briefly discuss on this, because for those external to our community, they might be surprised about why our data sets are so horribly small, and showing the plots, looking at the plots that Cosimo showed, seeing excess of 70 or 60, they might be surprised. So those are indeed photons, but in the energies that these telescopes operate, in the very high energy regime, the expected rates of gamma rays, it's extremely small. That's mainly the reason why these data sets are so small. Actually, the data describing the performance of your instrument, the instrument response functions, usually take more storage than your actual data. So the photons themselves, no. So for those of you external to our field, that is the reason why our data products are so small.
More questions? I don't know if anyone that is more experienced than us with FITS data would like to give us more feedback, because I mean, we have moved very recently to FITS data in gamma ray astronomy. So perhaps, let's say, astronomers at other wavelengths that have used them since a while can give us more feedback or their experience with it, if they're planning to move to others data support, let's say.
Jose Enrique made a comment. So in which of these data sets the model should be applied, the big or the small data sets? I'm not sure about which model Jose Enrique is referring to. Actually, let me very briefly go back to Bruno's point regarding DL4 and DL5, and then we go back to the Jose Enrique, because so this is interesting, because is there something specific to our high-level products that should be different in any way to the rest of the community? I mean, of course, our spectra are, let's say, very low statistics as compared with obviously optical spectra or even X-ray spectra. Yeah, there are like two conversations in parallel right now. So I know that that there has been some effort on standardization on also gamma ray spectra, but for example, for Fermi-Lat, Bruno, are you aware if some effort was done to actually try to converge with the rest of the community with other wavelengths? Such as spectra, light curves, etc.
Personally, I'm not aware of that, but I'm not a Fermi guy, so I cannot answer you correctly.
Yeah, this is certainly something to explore. Yeah. Yeah,
Okay, so they are making question on Discord, and they are rightfully saying that a question on Zoom get deleted. But if you ask them, if you raise your hand and speak, it will be recorded. So James actually asked us, what file format did gamma ray astronomy use previously? So for what concerns Fermi, Fermi had already the data released in this FITS format. So both the event list and instrument response function are stored in FITS file, like we do now. Basically, we took a lot of inspiration from Fermi. And instead, as I said, very high energy gamma ray astronomers were basically moved from particle physics experiment. And so they were accustomed to use root and C++. So for example, I'm a member of MAGIC, and in our experiment, we reduced the data to root files. Basically, all the data levels that I showed you in the table from data level 0 to data level 3 are embedded, stored in root files with different attributes. We basically use specifically root trees, basically. So each event has, it's an entry in the tree with all the properties like the direction, the energy, etc., etc. Does this address your question, James? Something else you want to ask? asking him to unmute himself. Okay.
Dirk also raised his hand.
Yes.
So
Well,
please,
since
Dirk.
nobody else is asking questions,
Please.
I can ask something minor. So what fit standard are you using? Are you up to date there?
Yes, I think it's the 4.0 for the one that we used for the joint grab release. Yes, so it's the latest one.
Yeah, I can only say this is a big and very nice step forward that you've made. It's fantastic. It's going to allow CTA to become a real proper observatory. Congratulations.
Thank you. In which waveband are you involved?
Well, I started in very high energy gamma ray astronomy long ago in the 90s. You might have seen my papers on Markheim 421 and 501 and so on. But then I was actually working for Fermi later, and then for Integral, and now I'm working for Alma.
For Alma. Okay.
And Alma has used exactly the same type of software stack, so to speak. I mean, we are also working with an analysis software that is C++ with a Python wrapper. It's called CASA. So it's all very similar in terms of the tools. However, for our data format, we are not using FIT, but some, so to speak, proprietary format. But never mind. So the only thing we store in FITs are really the images at the end. So I assume you also have tools then that create images. I mean, the actual astronomical images.
Yes, they're the high-level science tools.
And those are also using the proper standards and so on.
Yes, exactly. This is another thing why in general, I think both 3D analysis, but also this kind of visualization was never done in previous experiment, because now we have all these fantastic routines for astronomical libraries like AstroPy, and this was missing in the past. So I think this is also one of the reasons for which it was a bit more difficult in the past to do this kind of to produce maps or cubes in general. Because
so
when we do the data reduction in 1D, we do the classical 1D analysis with, I will share my screen again.
So the problem that the instrument is so strongly weather dependent, you have solved by having a per run or per, what do you call it, execution block, we call it in Alma.
Run.
Per execution block instrument response function, correct?
Yes, it's also to account for different, not only weather condition, because for example, there are other observational conditions that change the response function basically, especially for example, the zenith angle. So the zenith angle that you are pointing to will change the
I know.
The energy. So yes, exactly.
Yes,
so it is, let's say, a recipe to have a stable. We are more or less in the ballpark sure that in that 30 minutes the observation.
But I mean, the zenith angle dependence should. I mean, that's a parameterization that should not depend on the day the observation was made. That could somehow be generalized, no?
I don't know, because
can I step in, Cosimo?
Sure.
So this is a very good question. So it all depends on the systematics levels that you need, no? So for the current generation, so we essentially perform simulations on a given set of parameters, no? So in zenith and azimuth, for example, so you are observing Markarian, it's moving across the sky. You can have a closer to the simulation distribution of events to calculate your instrument response functions, etc. But for CTA, for the future observatory that will be using this format, the systematic requirements are much tighter. So we really want to go to the few percent level in systematics. So for that, doesn't matter that the zenith evolution in the sky will be the same every day, but for example, the different light illumination that you have in the sky that given night, or for example, the density profile of the atmosphere may change from one night to the next one. So the deeper you want to go into the actual systematics that you expect, it will become way more complex. So
I mean, you're definitely on the safe side by having simply everything just per time slot without trying to generalize.
Yes. So for example, Hess, I believe in the past, maybe Bruno can comment, but Hess in the past did some data releases, and actually they internally export all their data into this format, into this DL3, no? And when they do export all their data, what they do is they export their event lists on one side, and then their instrument response functions in another side. So they are not physically embedded into the same FITS files, okay? So then when they perform a gamma ray analysis, what they do is they, let's say, connect via software the specific event lists with their specific instrument response function. So you don't need to duplicate so many times the same instrument response functions for runs that will be relatively similar.
Yeah, exactly. That's what I would expect. That's kind of the way to go. Yeah. Okay. Thank you.
Bruno, please. You muted yourself.
Yeah, sorry. Sorry. Thank you. Thank you. Just to continue the answer of Tarek to Dirk. One thing that is interesting in this format also is that we have in the space mission define a good time of interval GTI. So this concept is very useful, I think, even for us, because as you know, the instrument response files, the instrument response of our telescope can change rapidly when we observe at low altitude. So due to the variation of the zenith angle. And then during our observing block, so which is roughly 20 minutes, 30 minutes, the response of the instrument can change significantly. So by introducing the GTI, and as proposed in this format, GTI, one interval is such that the instrument has a constant response. And so we can link in a unique manner one GTI to one IRF. So if within one observing block we have we notice that we should change the IRF change significantly, we can then able to create 2, 3, or 4 GTI within this observing block and link one GTI to one IRF. And I think this is also an improvement compared to what we have. Also, the interest of having an OB IRF, a runwise IRF, is the following. When we have major observatory like S or Alma, we know that we have hardware configurations that can change, telescopes that works or doesn't work, or that all there we are in the building phase. And so, the response of the instrument will evolve with time. So it's quite important in order to provide a good systematic level for the astronomer of our data to associate the correct IRF to the correct run.
Thank you. Matthias also wanted to intervene. Please, Matthias.
Yes, hello. But Actually, I would more switch topics. So I don't know if you want to discuss a bit further this particular point that you were just discussing, and then I chip in afterwards.
Let us give the give us the opportunity to bring a couple of questions from the Discord, and then we can give you the word. Is that okay?
Yes, sure.
Okay, so
yeah, so
James
for example,
asked if there is any idea that we can take from root that we should think about other formats for other formats.
Yeah, so I briefly answered in parallel. So the thing is that those of you that have worked with root, they might automatically think, no, there is no way that we can learn anything for astronomy. But I mean, root is strongly based on the basis of very quickly going through a list of events, and each of those, let's say, entry into a root file will have a very complex structure, let's say, no? And it is actually very useful and very efficient to do exactly that. But in astronomy, as it was briefly discussed before, usually what you want is an image or maybe a spectrum in some cases. But the root format, it has been really developed thinking about particle physicists, and in general what they need is a very deep set of libraries for accurate statistical analysis of those events, and which relates to another comment that Robert gave, which is just the anecdote of him not finding a fitting routine for his specific use case, and he found it in root, which is exactly it. So root is a set of libraries in C++ that actually are extremely useful for particle physicists, although I'm really not sure how much we can learn to incorporate into other formats. I really cannot think of that many cases in which maybe in X-rays and soft gamma rays we can definitely perhaps such a data serialization is useful, but again, like I'm not really sure. I'm certainly not an expert on that.
And then Sonal asked if the data format is frozen. It is not, because as I showed you, everyone can propose a change. So when other instruments perhaps need some other metadata or column, they can ask it to be added. And indeed, Utah commented that in KM3net, they're actually taking a look at the format and trying to implement it. So before going forward, let us let Matthias talk. Please, Matthias.
Yeah, thanks. Actually, my questions or my topics were a bit related to this last question. Yeah. So maybe just to comment also, for example, from the viewpoint of CTA at this moment. So CTA is currently undergoing several, let's say, revisions of previous definitions that we have been doing in the past years. For example, we are just now looking more closely once more on the definition of the instrument response function and how we describe it. Yeah. That would certainly lead to an evolution of the format, and what that might then be different to what is currently documented in this open gamma ray format, yeah, which we use as an input certainly also to define the data model, DO3 data model and upwards that we have for CTA, but we indeed also expect it to evolve. Yeah. So certainly for us it's not frozen, because in CTA we have not yet chosen the final format for the data model, so the content of DO3, but the format we expect to have it available in FITS format. Yeah. Which brings me a bit to the topics or the questions that might be a bit relevant for this session here, because you called it standardization of the DO3 format, right? And a bit what triggered me here then asking the question is what makes a format a standard? Yeah, and okay, that question is maybe a bit philosophical sense, but on the other hand, it has a bit direct implication because what could be nice also to discuss here in this forum is exactly these questions: how to evolve formats, especially when they have been initially driven by a community rather than by experiments. What are the stakeholders for exactly the gamma ray format? And I agree with Bruno that the whole multi-messenger and multi-wavelength community that would allow, and especially one of the drivers that you have not mentioned in your slide, interoperability, that is really important for this format, which is also for us important is CTA, because we want to position ourselves in the multi-messenger astronomy, right? So who are the stakeholders to include in the discussions, and what is actually the right forum to discuss further evolution of this format? Yeah, you certainly mentioned the Open Gamma Ray initiative, but is this the right forum, and how does it, for example, what is the role of the IVOA and the interaction with the IVOA that we might also want to look in the gamma ray community to achieve for standardization of a format? Yeah. So these might be, these are some questions that now popped up during this session also for me.
And can I answer briefly, Cosimo? So
Yeah, sure.
it is, so there are several points that you brought up, Matthias, but everything is related to right now 2 points. First, it is an evolving thing, so it is certainly not fixed. And the second one is to extend it to other event-based observatories. No, so there are like these 2 open questions that we are discussing, and also how to standardize it. No, which is the point that Matthias brought. I actually, so in our experience over these years, it simply did not happen that we were able to impose anything on anyone. Okay, so it always throughout the evolution of this data format or data model, if you want to call it, what happened always is that a given, for example, a given analysis software or a given experiment or a given use case appeared, and then we needed to modify the model slightly in order to incorporate this use case. No, so this only happens when the person interested in this use case raises up his hand, says, "Look, I need to do this," etc. And so the thing with standardization is very complex, because if I want to standardize something, then it is kind of an imposition to the surrounding analysis teams, analysis software, etc. So the which also relates to a discussion that we had in the very beginning of this Discord chat that you can actually go back and take a look, because Henrique was discussing about using DL3 with Hawk. No, so I'm seeing Marco answering standardization is not an imposition, but what I mean is that this data model, it's always coming from the people that need to use it and the people that need to do it. So I can put a very simple example that Matthias will easily understand. So if someone from internally from CTA, as you, Matthias, takes a look at the current format, he will automatically and instantly realize that it will not work for CTA as it is right now. Why? Because for example, the instrument response functions are not complex enough to describe for instance, the evolution of the instrument response functions at certain parameters that are currently not included. No, this is, for example, a very simple question to make. No, but the thing is that as soon as we have some CTA data, or as soon as we have some CTA simulations, including those parameters that are currently not reflected into the format, then we would create an issue, we would create a pull request, then we would incorporate that need into the format, making sure that there will be analysis tools that are able to also include that format. No, so for example, to include Hawk into this format, we definitely need Hawk people that step in and participate into the forum and into the discussion. Define also the changes that need to be applied in the analysis tools that will use this format, these files, and then making sure that both the analysis teams and the data production teams will make use of those changes, then it makes sense to change the data format. At least that is how we have worked until now.
Yeah, thanks a lot, Tarek. That indeed explains a lot, let's say, the process here. And certainly I'm not here to at all to criticize this effort, not at all, really, because you already showed in your talk, let's say, the benefits of such standardization. Yeah, it's really visible. You can do this kind of multi-experiment analysis, and that is really the benefits that is also experienced in other communities. And maybe I'm just asking this question a bit more to learn maybe a bit about best practices and experiences of other communities that had also to standardize on such formats before. So on how to organize such discussion and how to create a forum for the experiments and the community to discuss such further standardization.
Yeah, this is why I said that it would be really interesting to receive feedback from people that are actually using FIT standard since a while, but it seems that there is no one at the moment present. Because I guess other instruments have...
Well, that's not true. Sorry.
No, please.
I'm actually responsible for the FITS standard kind of implementation in Alma. And,
okay. So did you start for
we only
something
use it for
that...
images. So
okay.
This is different. In fact, I mean, let me tell you what it's like in Alma. So we have essentially 3 data formats. We have the archival data format. We have the working data format that is not really stored anywhere, but only used for intermediate products during processing. And we have FITs for images. And actually, we have 2 image formats. There's also an intermediate one used only during processing, but what goes into the archive are FITs images. So I think this is a situation that is very common in all observatories. I would also regard your new FITs format as some kind of export format, right? I mean, people are not working internally with this, or are they?
Yes, it's more of an export format for
that's totally fine.
For us. For Magic is more for the legacy data, let's say.
And the good thing about this is that, you know, if it's a FITs file, people can read it. That's for sure. If you follow the FITs standard, you don't need to talk about standardization anymore. Anybody who has a FITs reader can read it.
Exactly.
Just need to have CFIT.io or you know, some of the F tools or what. And there are also lots of Python tools to read it. So in a way, you are done. People will not get one of your files and sit in front of it as if it was a black box, that it's inaccessible.
No, exactly.
Totally look at it and can explore every corner of it. Question is then, how do you actually extract the image from it, which or the spectrum, which is the thing that you really want. So there you have to provide your not proprietary, but your own special software. And I don't know, that's probably going to be open source, right?
Yes, both the candidates are open source, GammaPy and Ctool.
Is it some kind of Python module, or how do
GammaPy is entirely built on Python. The other Ctools
Python 3 module.
Yes. It's an AstroPy affiliated package, so it's Python and it's AstroPy based.
Great.
The other Ctools relies on this gamma lib, which is a C++ library to read different gamma ray astronomical data. This is why it could combine Fermilab and the SCT DL3 together. And then there is a Python wrapper, but you can use it also as a command line tool. Like it's very similar to the classical F tools.
Great. So yeah, I think you are very close to the final thing somehow. I mean, the question is then only, to make your tools work. I mean, to actually deliver scientifically correct products, you need to think about what metadata does your tool need, and that has to be in your FITS file somehow, or in the instrument response function storage. And that is something only you know, that cannot be dictated by the community because they don't know the instruments so well. So there's some kind of part of the standard that simply has to work. And there you need very good versioning, I would say. You need to make your tools aware of the format version that it is reading so that it does the right thing with the right version of your instrument response function format and so on. So there has to be some part of the code that detects conflicts in terms of versioning, so that the code knows, okay, I'm capable of reading version
11,
1.3 of this FITS
data format, yes.
format, but I'm not able to read version 4, for example, and then it should stop and tell people, update your software. This is a too new file. And then you have all this problem of backwards compatibility. Does a new version of your software, is it capable of processing old data that have been downloaded 3 years ago, that were using slightly different conventions and all that?
So,
but
yeah,
it's
so
definitely there are solutions for that.
sure.
Yes.
Here, for example, we have Jose Enrique, which he's actually have been working on the provenance aspects of the future CTA analysis. So he might be able to give some insights on it. So I want to very briefly discuss about what you were saying, and also which also connects with some of the discussion that we have right now on Discord. So I would say that more than the format itself, like technically the format of how you are storing those bytes of data. So this is more of an effort of defining the data model that we need as a community, in the gamma ray range, let's say, and this was never done before. That's why it's being done now, which is interesting, and precisely because it is not so hardwired with the FITS data format itself. Some of the discussion, for example, here people is discussing HDF5 versus FITS. So this effort still completely makes sense. So it still makes sense to continue identifying how and what needs to be stored, because going from a FITS standardization to any other, to HDF5, etc., would still, in any case, strongly benefit from this initiative. So it is not so much the format, but the data model that has most of the value, at least in my view. And the second point regarding provenance, etc., this will actually be a challenge, because I really foresee in the coming years that many of the current generation Cherenkov telescopes will either stop operating, or operate in a different manner, with CTA as the main observatory in our field. And as Cosimo has presented, it is expected that they create some legacy data products. No, so we do not expect that those legacy data products will strongly evolve with time. So it seems likely that these legacy products from the current generation will more or less halt in time, at least their format, while CTA will surely evolve. No, so as you were indeed saying, making sure that the software properly takes that into account, and we really need to make sure that the software handles different versions of the data format will be crucial, mainly to use all the archive data of the current generation of telescopes.
Yes, if I can go back also to one of Matthias' points that Dirk was also discussing. So Dirk, you said that you store image. So basically the format that you have standardized, I think it's even higher level than the one we are storing, right?
Well, as I said, we have an archival data format that's called the Alma Science Data Model that was developed for Alma and the Very Large Array, and is, so to speak, really special. It's an XML plus binary format. That's our raw data. And believe it or not, it's also essentially a list of events. So there's a big similarity to the Cherenkov telescope data. That is what we use for this part, and that is really large data. I mean, that is can be terabytes.
And connecting to one of Matthias' points.
That is from the archives. And then there are these intermediate data formats that are only used during processing and never really stored anywhere long term. Called the measurement set, never mind. And then at the end, the other archival products are images. And that's where we use FITS, because that's what is really the astronomy standard at the moment. I mean, nobody uses anything else but FITS for images.
And this data format, how was it defined? Is it something internal to Alma itself, or does it share commonalities with other telescopes? Because, for example, you're using the same software, no?
Well, the ASTM, yes, CASA was originally developed as the designated package for Alma and the VLA, and it still is, but it has also the ambition to be a general tool for all radio astronomy. And the ASTM came after CASA was already developed, so to speak. The ASTM was developed as part of the Alma project, hence the A in ASTM, and in order to save resources, VLA also adopted the same data format. So
and how was it defined?
Came together and put in a reasonable amount of money to pay somebody, or actually a few people, to develop this format.
I see.
Based on a precursor, which is called the measurement set. This is something that was developed by the radio astronomical community and published in its second version in 2000. So it's a properly documented format, but it's really only a model. It doesn't really say anything about the implementation, meaning the underlying file format that is used on disk. It's only the design of the database, essentially.
And it was not community driven, as you said. There were
yes, it was community driven.
But as you said, there were these two people hired to
okay, but they took essentially this measurement set, which was a community. Well, I mean, it's not like they did a survey of all radio astronomers and asked them what they think it should be. And
exactly. That's the point.
I mean, there's only one truth. It's a mathematical problem that has one solution, essentially. And the fathers of the measurement set came up with that solution, and it has proved now over the last 2 decades to be amazingly correct. I mean, nobody has really found any hole in this design yet. There have been not even extensions were really seriously necessary, and the ASDM generalized it further to make it applicable to really all thinkable radio telescopes. And also here, a pretty good job was done. So this is a database that has something like 50 tables, and it really covers all thinkable bases. Only very few tables had to be added in a second iteration, like over the 2 years that followed the inauguration of Alma. And now it's very rare that any addition is made to that format. So I don't think you can design something like this by committee. You have to really get people who know what they're doing and you know, have the whole idea and the whole concept in their brain and nail it down. That if you get the right people to do this, that the result is normally better than if you know, lots of people just dedicate 10% of their time to think about this now and then. You need to have some people who really work hard and full time on this to really think it to the end. At least that's my opinion. And then, of course, you have a proposal, and you can distribute this to a larger group of people to get feedback, and maybe some people will still discover some small problems in it. But the big design has to be done by a small group. Otherwise, it takes forever, or it will be some kind of Frankenstein thing that is not quite right.
So
Yeah.
Dirk, or if I may interrupt, so what he describes, the parent of everything is this thing called the measurement equation, which in principle should apply to gamma ray astronomy as well. But I've not seen it applied to anything outside of astronomy. So the mathematical foundation of how radiation is modified by the instrument is the measurement equation, and it should capture gamma ray.
That's true. Yeah, maybe the measurement equation is even applicable to gamma ray astronomy. I mean, we don't have.
Well, it should be, yeah.
Yeah, possible. I mean, a gamma ray observatory is not an interferometer at all. It's
No,
yeah, exactly.
no.
The point is that we detect like particle hits.
It's just counting events, and the secret is really in the response function. How does your detector respond to gamma radiation coming in from a sources at infinity, so in parallel tracks essentially, and then there's the other thing, that's the background. So this background model that you're mentioning, that's also a big difference to an interferometer. So
Yes, because in many aspects
could maybe be applied, but that would not be the whole story.
Yes, because in many aspects we are much more similar to a particle physics experiment. So we basically detect particles fundamentally. So
you are a particle physics experiment. It's just that you don't control the accelerator. I mean,
exactly.
Although if you think about it, it's not that different to a CCD camera, no? I of course not talking about interferometers, but CCD cameras are like effectively counting photons. So I mean, come on, it's something similar, no? In the end, it everything comes to a given quantum efficiency, which is our effective area. It comes to a direction. It comes to a given resolution. Of course, we measure simultaneously direction and energy, although we have enormous errors on both, while optical astronomy generally either does one thing or the other, no? Generally, this is starting to change now. But in principle, it's not that different. The problem is that first, our detector changes constantly, no? The performance of our detector changes minute by minute, which in a CCD camera usually does not happen. Usually the only thing that changes is the transparency of the atmosphere, very roughly, of course. You can include seeing, etc. But our detector itself changes because the atmosphere is our detector.
Even that is, for example, Alma has the same thing. I mean, we are permanently observing calibrator sources as references to account for changing conditions. We have a constantly changing detector in an interferometer. It's just the same on a second basis. It's very similar.
Yes, so we should definitely learn from what Alma is doing.
No, I mean, you have got your solutions. I mean, you've been doing this now for several decades, and I wouldn't. I mean, the big change of paradigm. I mean, I remember when I was working in this high energy gamma ray astronomy, I was not using root but PAW, which was the predecessor of root, and we were also using these n-tuples. Actually, I introduced that, and this worked very well. And the big difference is that you are much more forced to rely on simulations. You don't have reference sources that you can jump to and quickly check the state of your instrument. There is essentially with a high precision, there is no reference source, not even the crab, because we know now it's also variable, right?
Yes.
And the crab is not up all the time, so you have really no reference that you can fall back on, and therefore you need to use simulations to a much larger extent than other fields of astronomy. but I guess if you have a big set of simulations parameterized by different atmospherical conditions, it should be possible to cope with that. I mean, as far as I can see, you've got the solution already. I don't think you have to adapt too much to other fields of astronomy. You have very specific conditions, and you can, how shall I say, be self-confident enough to use your own methods.
Yeah, so
if you package it properly, it will be fine.
So the key here is going from experiment to an observatory, no? So that's the main step for us, and certainly a lot of work needs to be invested into this, because it is clearly not ready yet for several, for example, observing modes that CTA could have, or several other things. But the key aspect here is that the decisions, let's say the most important decisions, I think that are already taken. Let's say it will be fits or HDF5 or equivalent, but containing event-wise data plus instrument response functions, and that is the level that we will be, let's say, opening to the community, sharing, and that will be the input for science tools. So as all this has been already, so everybody converged on this, etc. So then all the probably more complex technical details, which include what you were discussing about all the Monte Carlos required for a decent calibration. As you were saying, our instruments literally cannot be directly calibrated. so we need to rely on a whole complex system of calibrators, which I could bore you for hours. But yeah, at least regarding to this, let's say, data standardization or data model standardization, it seems that at least many of the problems of the technique will rely underneath internally into CTA, and the user, the future guest observer and science tools user will essentially not feel the difference with for example, other fields of astronomy. So they will not feel, at least will not dramatically feel the difference between using, for example, Fermilab data or CTA data. That's our main objective, no? And by incorporating both the event lists and the instrument response functions, as by defining, for example, the good time intervals that Bruno was referring to, etc. By doing all these tiny things, we expect the process to be quite uniform. So it will be a relatively simple, well, not simple, but a relatively similar analysis as the one that is currently being employed in the high energy astronomy field. So I guess that is good news. And Cosimo, we're getting near to the time of the.
Yes, I think we have 3 minutes, right?
Yes, indeed. Yeah. So that's why I was putting the camera on, just to remind you that. Sorry, that's my duty.
No, don't worry. I think Marco wanted to talk. He had the hand raised for a while, so maybe we can take some comment from Marco.
Yeah, sorry, I didn't want to interrupt you because you were having a really good discussion, so no need there. I just wanted to clarify my view that is, of course, biased by the work that I'm doing. And I think that the format that you are developing and dealing with, it's really a good one. And the way that you are tackling the solutions for formats, how this is used, what software do you attach to it, what communities you can involve, what projects or experiments you are able to attach to. This is already great. I think it's really at a good major level. So if you are, I think that what you are dealing with now is tackling the interoperability with other, let's say, domains of observation in a sense. So multi-wavelength, multi-messaging, it's always in that it's in the same direction. So if you want interoperability there, you have to explain to the other communities what are your needs. So the IVOA approach there, of course, comes from the sky, from the night sky observation. So it has simple basic requirements at the start. It had simple basic requirements at the start that were positional in the sky, bandwidth, descriptions, and things like that. So 4 major axes, if you want. So to positional, spectral, time one, polarization, you have possibly similar needs, but written in different ways. And the fact that you are pointing to, that you explicitly said more than once that you have event lists that are what I think in the IVOA are modeled or can be modeled in the sparse cubes. Well, that's some use cases and requirements that I think the IVOA will be really happy to listen about, and maybe we can join efforts at that point, because the format is fine for archiving, for analysis, for whatever. Then you have to make it well. Now again, buzzwords. You have to make it discoverable. You have to make it interoperable, and at that point, you'll have more software instruments and tools that can deal with gamma ray and other data together. Just a clarification. My intent was not to criticize anything.
No, thank you.
In fact, I mean, I don't know if maybe, I mean, if this channel can be left open if you want to continue to discuss, or if you want to continue the discussions on Discord. I mean,
yeah, I think we can continue on Discord. Also because me and Tarek are supposed to be in the Magic meeting in the meanwhile.
Okay, yeah. I also have a similar problem. I have to be in another meeting. Okay, so do you want to give a final word, Cosimo or Tarek?
Well, thank you very much. I think there was a good participation and nothing. Thank you.
No, I'm actually positively surprised. All the discussion we had, like we were worried, like there would be like cricket sounds everywhere. No, it was very
luckily there
interesting.
was Dirk that he passed the entire electromagnetic spectrum, so he could comment on.
Okay. Very good. And I have a little message from the program organizing committee on the log. So to ask everybody to check the poster channel in Discord, because there is some info there about how to sign up for the lightning talks today, for the dedicated poster lightning talk session, which is later on today. So this just so please go and have a look at the poster channel on Discord, and you'll find all the information there.
Okay.
Okay. Very good. Many thanks, Cosimo and Tarek, and all the people for participation.